I'm very pleased that our first speaker is Professor Anna Scaife from the University of Manchester, where she's Professor of Radio Astronomy. And she's also head of the Jodrell Bank Centre for Astrophysics Interferometry Centre of Excellence. So Anna, if you can share your screen, hopefully that's possible.
Does that look okay?
That's great. Yeah, thanks, Anna.
Okay, brilliant. Gosh. Thanks, Graham, and thank you very much for inviting me to talk today. I'm going to talk about big data with the Square Kilometre Array, which is the world's next big radio telescope. So I'm assuming that perhaps not everyone has heard of the SKA at this point. You know, I tend to live in a bit of an astronomy bubble, so I'm going to give a brief introduction. So the SKA project itself has been rumbling on for a very long time internationally, but there was a key turning point a couple of years ago now when a number of countries got together and signed a treaty convention to build the Square Kilometre Array Observatory, which would provide a large-scale international radio telescope to address some key science goals, which I'll talk about very briefly in a second. Whilst this happened in 2019, treaties take a while to ratify, and in fact the treaty has now been ratified, and the treaty organisation comes into force this year, and in fact came into force last month. So the SKA now exists as an intergovernmental organisation for astronomy in the same way that the European Southern Observatory, or CERN, exist. The purpose of the SKA was to address some of the highest priority science goals in radio astronomy. And so just to give you an idea of what those kinds of things may be, on the top left, you're seeing a simulation of how the first stars in the universe were born during a period known as the epoch of reionization. This is something that we know something about, but don't know anything about in detail. And the SKA is designed to map this region of cosmic history. And in fact, this was the first original driving science case for the SKA, and it's where the name comes from, because someone worked out that you need the sensitivity from a square kilometre of collecting area in a radio telescope to detect the epoch of reionization. But of course, when you build a very large radio telescope, you can also investigate a range of different science cases. And so on the top right, you see the hunt for gravitational waves, which can be mapped through the time domain signals from rapidly rotating neutron stars known as pulsars using the SKA. On the bottom right, you can see the science case on exploring the origins of cosmic magnetic fields, which are a phenomenon that we see ubiquitously across the universe, but we haven't really constrained how those magnetic fields came to be where they are and at the particular strength they are. And then, of course, bottom left, and many people's favorite, is the search for life on other planets. So using the spectral capabilities of modern digital radio information to search for molecular lines from other planets and use those to answer the question, are we alone? And so with these driving science goals, a set of requirements were put together to build, to design the radio telescope. And in fact, the conclusion was that we needed not just one, but in fact 2 radio telescopes. And the first of these will be situated in southern Africa, in the Karoo region of the Northern Cape. And this would be what you might think of as a more traditional radio telescope made up of dishes, such as you might have seen at existing radio astronomy observatories, or perhaps in the film Contact, if you're around the same age as me. And there would be 197 of these dishes stretching across southern Africa, forming what's known as a radio interferometer. I'll talk a bit more about that as we go through. The second site is still in the southern hemisphere, but on the other side of the world, in the red deserts of Western Australia, one of the most sparsely populated regions in the world. And that, of course, is the reason for siting a radio telescope there, because of the lack of radio interference. But this one looks quite different. So this is a telescope designed for very long wavelength radio astronomy. so meters to tens of meters of radio waves. And you can see that it's composed of, well, thousands, about 130,000 individual radio dipoles that are phased up to create the equivalent of a radio dish. So you can see each one of these clusters of antennas and think of it as the equivalent of a single radio dish, but one that operates at very long wavelengths. And anyone who's particularly interested in digitization is probably thinking about the signals from these antennas already and how vast they must be. So whilst I've been showing you some artist's impression, of course, there is already hardware on the ground at this point in the project, in Western Australia and in Southern Africa. So this is the Meerkat telescope, which forms the first 64 dishes of the 197 dishes of the SKA phase 1 in Southern Africa. And this is a telescope that is up and running and observing and doing some of the most cutting edge science in radio astronomy already. And it's able to do that because when you build a radio interferometer, as soon as you have 3 dishes on the ground, you can start using them. And every time you add an extra dish, you just integrate it into the array. And so it's a very efficient way of building up scientific capacity. And of course, it means that people get to use the data quite early on in the process. So I just wanted to say a quick word about how these arrays operate, because it will hopefully help to explain the data flow as I go through that in a couple of slides. So for radio telescope arrays like these, we don't typically look at the signals from the individual dishes in the array. Although the sensitivity in the collecting area is determined by the total surface area of the dishes, in fact, the imaging is done in a Fourier scenario. So what we actually do is we correlate the signals from every pair of dishes in the array. And those provide Fourier components of the power distribution on the sky in the radio spectrum. So for short spacings, we refer to spacings as baselines. For short spacings, we're measuring small Fourier frequencies, and therefore we're recovering information on larger image scales. And with longer baselines, we're recovering larger Fourier frequencies and therefore smaller image scales or finer details. So as you build out your array, which is what you can see in the top left, you increase the resolution of the images that you can finally make. Although, of course, those images do have to be formed using a Fourier inversion process, which is quite computationally expensive. The other thing that this means in terms of data flow is that however many antennas you have in your array, say n antennas, the volume of data that you generate doesn't scale as n, it scales as n squared. So your data rate increases very, very quickly the more antennas you include into the array. So hopefully now I've explained a bit of the technology that we're using and motivated the fact that the SKA is an instrument designed to answer some of the most important questions in modern astrophysics. But the other aspect of the SKA that we can never forget is that the SKA is also a big data machine. So with that in mind, I thought I would take you through the data flow of the SKA using this nice visualization from the Signal and Data Transport Consortium of the construction packages. So if we take the 2 telescopes of the arrays, then each of the dishes have 100 gigabit per second data link from them. And so the dishes together produce about 20 terabits per second of data. The antennas in the low frequency array produce of order 10 terabits per second. And that is actually quite a reduced data rate already. If you took the raw data rate of all the dipoles in the low frequencies arrays and combined them, then you'd be storing about 5 zettabytes of data a year, which is just ridiculous. So of course, we're not doing that. The data are sent from the antennas to what's represented here, which is the central signal processing facility. And that's where the data are correlated, which includes corrections for the separations of the baselines in the array, so geometric separations, in order to correlate the signals correctly. Those separations have to be calibrated using a distributed clock signal to all the antennas, which is done at very, very high precision, so atomic level precision. The data are then combined in central signal processing to form those correlations that give us the Fourier components. And so the data kind of explode at this point. However, we do perform time and frequency averaging, which reduces the data rate down again. So at this point, we either have correlated data for the imaging, or we have still raw data for time domain. And those data are sent to what's known as the Science Data Processor. And this is where the products that the astronomers will actually use are created. So for imaging, a product might look like this, remembering that we don't just have, the image on the sky, we also have a very large number of frequencies. So there's a spectral dimension to the data. So the data are in fact cubes. And in fact, at this point, those data cubes, which are sent around the world to astronomers in different places, those data cubes can once again be bigger than the raw data themselves. Given the resolution and the field of view of the SKA mid instrument, the South African instrument, in fact, those cubes could be sort of 2 to the 16 on each of the image axes, and then about 16,000 frequency channels. And that is irrespective of the length of the actual observation on the sky. So for a snapshot observation, so where we just point the telescope, grab some data, and then turn it off again, there might be quite a small amount of data flowing from the telescope to the Science Data Processor. But then at the Science Data Processor, where we make the image cube, the dimensions of the image cube remain the same. And so they can easily reach a petabyte for a single image cube from only a few seconds of data. And of course, then individual astronomers have to be able to use those data. So to just give you a bit of a more of a geographical representation of this, the data from the telescopes are sent to central signal processing. Originally, the central signal processing was expected to be co-located with the telescope. However, recent engineering changes, in fact, very recent engineering changes, now mean that the central signal processing has been moved closer into the what you might think of as the host cities for the instruments. So for South Africa, that would be Cape Town, and for Western Australia, that would be Perth. And so now we're sending those sort of 20 terabits per second over about 800 kilometers to get to that central signal processing, which in itself is a challenge. Originally, the central signal processing was co-located with the instruments in order to minimize the data transport. However, the maintenance and the, if you like, the day-to-day operations of those processing facilities are much easier, obviously, if you have them co-located with urban centers. So a decision has been made to change that and to move the data closer to the science data processors, which were always intended to be in Cape Town and Perth. Once the science data processor produces a data product, say that image cube that we saw in the previous animation, that image cube then has to be delivered to astronomers, or if not astronomers, then to the partner countries of the SKA network. There are currently 15 partner countries in the SKA organization, and it's actually growing slowly to include more and more different nations. So each of those countries needs to be able to receive data. And the way that the science data processor works for the individual telescopes is that it's not accessible to individual astronomers. So I, for example, would not be able to, send a query directly to the SDP in Cape Town to ask is this data set available? Instead, the data are expected to be delivered around the world to a network of different computing centres, which are known as the SKA Regional Centres. And for that purpose, the observatory has costed into its operations framework dedicated submarine cables. So these are submarine cables with 100 gigabits per second data rate from South Africa that lands in Paris or London, I forget which, and for Australia it lands in Singapore. And then the data have to be transported around the world using more standard networking options, although obviously in the ideal situation those will be configured to allow for very high data rates, because latency is a problem in that case. So in order to simulate this data flow, it's been quite difficult. So I thought I'd just give you one example of how people have been addressing it. And this is a particular example from our colleagues in Australia, in collaboration with the Shanghai Astronomical Observatory and the Oak Ridge National Lab, who used the Summit supercomputer to simulate the data flow from the low frequency antennas, which are the Australian component. So obviously they're very interested in the data flow there. And they simulated the signal from the epoch of reionization, and then they simulated the response of the telescope as well. And they parallelized this by simulating a single frequency at a time, and then stacking those and coordinating orchestrating the flow of data for each of those channels through the Summit supercomputer. And the software that does the simulation of the telescope array here, is known as OSCA, was produced by the OERC at Oxford. And doing this, they were able to simulate end-to-end the data flow from the antennas right up until the imaging at the Science Data Processor. And if you want to read more about this, there's quite a few nice articles about it, including in Inside HPC. And this used some particularly nice tools that have been developed for the SKA, as well as other things, including the Deluge framework and the speed transfer protocol, that's speed with an A. And this was the result of their simulation, which produces a frequency cube that shows the evolution of that epoch of reionization, the birth of the first stars, ionizing the neutral hydrogen of the early universe as a function of frequency. So in terms of the total data volume being produced by the arrays, the expectation is that it will be about 2 petabytes a day. So conservatively, we normally round that to about 600 petabytes a year, but in principle, given the 100 gigabit per second links out of the SDPs, it could go up to about 720, 730 petabytes per year, which is large by anyone's standards. So I'm just comparing it here to some numbers, which I do admit are slightly out of date at this point. But it's certainly large compared to existing radio observatories. So the LOFAR telescope in the Netherlands has the highest data rate presently, which is 25 petabytes per year. And the 5 big experiments at CERN produced about 73 petabytes a year in 2017 when I got this number. By 2027, when the SKA is producing this volume of data, of course, CERN Run 3 will also, the LHC Run 3 will also be producing about an equivalent amount of data. So the storage and processing issues that the SKA is facing are shared by many other scientific collaborations. So just a word about those regional centres in the different areas. There have been a variety of design studies done to look at how the data flow will work within these regional centres, because the regional centres have to act as more than just an archive for accessing data, with a petabyte scale data set, astronomers are not going to be able to download it to their laptop and process it locally. So there has to be processing co-located with the storage. And in particular for Europe, we've assumed that the European Regional Centre, the design study for which is this AENEAS project that you can see the logo for at the bottom here. So the European partners of the SKA contribute about 50% of the project overall. And so we assume that Europe would want to store a complete copy of the archive from the SDP. So Sean, I hope this answers your question. But then of course we want a redundancy in that. So we have assumed actually that the redundancy will come from copies in other SRCs, because just arbitrarily multiplying things by 2 when you're at the scale of 700 petabytes a year is really quite difficult. And in fact, if you scale just the data that you expect from the high priority science objectives, so not including things like general observing on a what we call PI basis in astronomy, so individual proposals for observing time, then you're looking at an archive that should be of the scale of around 8.5 exabytes in the first 15 years of operation. And of course, those data are not just including the raw data produced by the telescope or the data products produced by the telescope, but they also have to catalog secondary data products. So we also have to implement the archive in such a way that it's also able to preserve the history of each of those secondary or advanced data products in terms of the processing that's been done and the original telescope data product that was formed the basis of that. And so the expected compute that's required to do that, certainly for Europe, given the proportion of European astronomers involved in the SKA, is around 26 petaflops sustained compute, which is roughly 10% of the compute that's required for the science data processor in the host countries. Which is around 0.2 to 0.3 exaflops. Now, obviously, there's a whole range of assumptions that go into those numbers. And so if you are interested in those, I can provide a link to the AENEAS website. All of the documentation is publicly available online, and it includes the full design model for the regional centre compute. So I think I may also have already said this, is that just the regional centres will need to be able to replicate the processing that happens at the science data processor, as well as including post-processing. So the reprocessing is really all about calibration and imaging. So calibrating the data from the telescopes and providing those image cubes. Any post-processing beyond that has to be done at the regional centres. So that could be as simple as identifying all of the astronomical objects in the cubes, which sounds simple, but when your cube is a petabyte, everything is complicated and everything is very computationally expensive. And I just wanted to highlight a particular aspect of that, which is the fact that whilst the SKA is expected to detect hundreds of millions of different astrophysical systems, it's also expected to detect new things. And in fact, if we look back historically at previous astronomical observatories, the things that they become famous for are usually not the things that they were designed to observe. They usually become famous for the things that they discovered. So we also have to preserve that discovery space for the SKA. And that is built into the data transfer out of the telescopes in a way that I can describe if anyone's interested. But beyond that, there's no way that it can be done by eye. I heard what someone say that there may well be enough grad students in the world, but there definitely isn't enough coffee to do it by eye. So it needs to be done in an automated fashion, which is why I just want to throw in an AI shout out here very quickly. And then the final thing that I just wanted to mention, which I think is pertinent to this meeting as ExCALIBUR as a UK program, is that, of course, the headquarters of the SKA, the International SKA organization, is located here in the UK. The telescopes may be in South Africa and Australia, but the global headquarters, that intergovernmental organization, is at the Jodrell Bank Observatory in Manchester, or near Manchester. And I think I'll end there and potentially take some questions if there's time, or reply to questions in the chat. So thank you very much for listening.
Thanks very much, Anna. It's absolutely fascinating. Yeah, I think let's have a look at the, there's a couple of questions there, Anna. I guess the second one requesting a link.
Yeah, I can probably hunt out a link to the speed data protocol.
Okay, thanks.
Yeah. And yes, so the data rates, just to answer Sean's other question, that all of the data rates that I've been talking about are specific to the SKA, so they don't include any contributions from CERN or ITER. But perhaps you're suggesting that ITER will also have a comparable data rate. Yes, I wasn't aware of that, but I can quite believe it.
Could you say something about the data storage challenges? The data rates are phenomenal. I'm sort of mind-boggling about the storage issues.
Yeah, so in terms of, there's a number of issues, especially around the regional centres. So in terms of the volume, it's actually not insurmountable. So that the numbers that I quoted around 8 exabytes is ramping up over 15 years. So there's time to build in that capacity. I think the greatest uncertainty is the cost of storage in that. So actually financially planning for it is the most difficult. In terms of accessing that storage, in fact, orchestrating a federated data management system across the regional centre network is probably going to be the most important bit, I would say. So we have been doing some early work on that. Obviously, the WLCG does a lot of this kind of federated shared data management. So we've been looking at the different DMSs that CERN use. The current favourite amongst those is the Ruscio DMS from I believe from the Atlas experiment, and that's not only because of the way that it operates, but also because of the way that it scales. So in terms of not just the volume of data that it currently manages, but also the number of individual data objects that it manages, Ruscio is certainly the leader as far as we can tell at the moment, and that work is being done by the SKA office themselves as part of the EU Escape project in collaboration with the Ruscio developers.
Okay, so I don't know how easy these are to answer, but a couple of related questions about detecting things we don't know about, detecting the unexpected.
Yeah, so this is a whole other talk, Dave, which I'd be happy to give sometime. It's actually what I do a lot of the time, is how you design AI solutions that can tell you about things that you don't know were there. So, one of the problems with a lot of AI solutions is that they don't provide calibrated uncertainties, and therefore it's very difficult to identify out of distribution events. So the plan at the moment is to work along those lines and to develop AI that's very sensitive to out of distribution so I would say sort of peripherally in distribution events.
Okay, keeping an eye on the clock. There's just a comment here from Scott Klasky, who's going to be speaking after the break later, to say that his group at Oak Ridge was was working with the SKA and Summit using Adios, which he's going to be speaking about later.
Yeah, he probably knows many more of the details than I do about that run. I just thought it was super cool, so I put it in.
Okay, so maybe a couple more questions in the chat. You could
yeah, shall answer in the chat.
Yeah, thanks, Anna. That's fantastic.